Yeah, do it. Yeah, these chairs are like way easier to tip over than you realize, you know? There's never a semester that goes by without somebody like dramatically tipping one of these over in the middle of class. It's very, very frightening. It's very loud. But anyway, I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for this class and just ask you to be with us today. Help us to glorify you what we do. And just guide our steps today, Lord. In your name I pray, Lord Jesus. Amen. All right, so I handed back the quiz. And again, I hopefully have a solution to that posted soon so you can see a representative example of, like what a good solution looks like. So some of you are further, some of you are closer, and so some of you have more points and less points. Anyway, let me just shut up about that. Let me look at another proof here. So example 1. Here's the assertion. Claim the sum of two rational numbers is a rational number. All right. So how would we prove this? Here's how it goes. Let x and y be elements of the rational numbers. All right. Then there exists a, b, c, and d in the integers such that, let's say, b and d are not equal to 0, and x is equal to a over b, and y is equal to c over d, right? So it's important that when we're talking about integers, we're clear on the point that the denominator is non-zero, right? And it has to be a fraction of integers, all right? So, let me chase a rabbit here for just a second in the middle of this proof. So pi, right, is the ratio of what? Classical geometric definition of pi is what's the ratio of the circumference to the diameter, right? Oh, so pi is the ratio of two numbers. That makes pi rational. What's the problem with this argument? Yeah.
The circumference and diameter aren't necessarily integers?
That's right. The circumference and the diameter aren't necessarily integers. And apparently, if we could prove that pi is irrational, that is to say not rational. It's unfortunate that rational and irrational sound so same to the English ear, like in the language. But if we could prove pi is not rational, then that proves that there does not exist a circle that has perfectly rational circumference and diameter. It's literally impossible if we prove that pi is not rational. Now you might wonder how you would prove pi is not rational, right? But I'm going to stop chasing this rabbit and get back to the proof. So we've got x and we've got y. Now what is my goal? I want to show the sum of two rational numbers is a rational number. Thus, x plus y, what is that? Well, that's a over b plus c over d. And then what do? Remember algebra? So AD plus BC over BD, right? Note that AD plus BC and BD, these are both rational numbers. And since B and D are not equal to 0, we know that BD is also not equal to 0. Thus, x plus y is an element of the rational numbers. So there you go. Any questions? Does this make sense to you guys? So this is like a for all proof because the claim is for any two rational numbers, right? Like if I was to write what we just proved symbolically, it's this, right? For all x comma y in Q, right? X plus y is an element of Q. This is what we just proved. And the proof of an implication, a for all statement, we have to assume we have an arbitrary pair, right? I can't just say, well, consider a half and a third. If you add them together, you get 5/6, right? That's lovely, but that doesn't prove this. We have to take an arbitrary pair of rational numbers to prove this assertion, and that's what we did. A related but different question is as follows. So example 2 actually builds off example 1. And here it is. For x and y in the real numbers, all right, if x plus y is irrational, then either x or y is irrational. So the proof of this rests on example 1, actually. Let's see how this goes. So what do you guys think I should do here? We're trying to prove that, let's see here. I guess we can suppose that x plus y is not an element of the rational numbers, and both x and y are elements of the rational numbers, right? So what kind of proof is this? I'm assuming that, you know, you see here we're saying either x or y is irrational. So if I'm assuming both x and y are rational, I'm assuming the opposite of this, right? I'm assuming that, in fact, you know, neither x nor y is irrational, which is to say that they're both rational, right? But then what? By example 1, what do we have? X plus y is an element of Q, right? Which is a contradiction. Thus we find a contradiction, and so either x or y is an irrational number. Yeah.
Is saying either x or y the same as the logical or? Or would it just like, because it's like, is that like the same as, like, is that like the plain English version?
I'm just copying it out of a book, so, but let's think about that. Let's see here. X and y real numbers. X plus y is irrational. Then either x or y is irrational. I mean, I'm relatively certain that we cannot say that we rule out the case that both x and y are irrational. Like, for example, I'm pretty sure that pi plus e is not a rational number, right? but they're both irrational.
Yeah.
So I think this is one of those places where the English actually means the mathematical, or, yeah. So I'd prefer actually then to change the wording from the book. Let's make it more clear. How could we do that? If x plus y is irrational, then let's just say x or y is irrational. Now we all agree. Excellent question. So I like this. This is probably part of the reason Dr. Sprano stopped using this book. We used to use this book before. It's The Transition to Advanced Mathematics by Smith, Egan, and Andre. And it's a good book. It's very readable. But there are some little, not quite, like in the proof, for example, here, this is from page 59 of, I don't know what edition this is, 6th edition. This book is in like its, who knows, 11th edition or something now, right? I'm sure the bookstore would be happy to sell you a copy for $200. But, in here, they have a proof that x plus y is rational, given that x and y are rational. And in their proof, they get to ps plus rq over qs, right? And then they say, since p plus rq and qs are integers, x plus y is a rational number. Like, I would take points off a student if they said that, because they have failed to emphasize a very important point, namely that the denominator must not just be a rational number, it must be non-zero. If it's not non-zero, it's not a rational number, right? It's just not even defined. So, none of us are perfect, but when you have those kind of defects in the book, it's troubling. You're like, well, look at your notes. Fair enough. But tell me about those defects when you find them so I can fix them. I will fix them. Any questions before I go on? Let's see here if I got another proof for us. Just a second. I got this sheet I wrote a bunch of proofs on, and I've done most of them. I got to find the ones I haven't done. You don't want me to go in reruns, right? Yeah, those are not the one. All right. I don't think we've done this one yet. So this is my example 2.41. Example 3. Here's the claim. Let x be an integer. All right. If 8 does not divide x squared minus 1, then x is even. So this notation here that I just used, I don't know if we've seen this before in here, right? But this right here means 8 does not divide x squared minus 1, right? So what kind of proof are we up against here? We're up against a direct, well, possibly a direct proof, right? But let's use contraposition, proof by the contrapositive, if you like, to try to do this one. So we're going to let this be, basically, this is my p, and x is even is my q, right? And we have a tautology. What does it say? It says that p implies q is logically equivalent with what? Not q implies not p, right? That is, proof by contrapositive uses this tautology. So let's do it. Let's try it. We assume what? So proof looks like this. Proof, suppose suppose x is odd, right? We proved last time that an integer is either odd or even, right? So if it's not even, it's odd. Okay? So suppose x is odd. My bad. Maybe a little more precise here. X is an odd integer. Then there exists m in the integers such that what?
8 divides x squared plus 1, or minus 1?
Nope. We can't say that. That's what we're trying to prove. If you say that at the start, I will take your points away. I don't want to, though. I've got enough points. What's that? X equals 2m. But what did we say? Did we say x was even? Okay, yeah, I forgot. I left my glasses in my office. I really can't read it from there. My memory is short, so I forgot. But yeah, odd. So x is equal to 2m plus 1. Great. Right? Then consider, we're going to look at what? X squared minus 1, right? And there's various ways we could go here, but one of the ways I like to do this is to use algebra. So x squared minus 1 is x plus 1 times x minus 1, right? Which is in fact equal to 2m plus 1 times 2m plus 1 minus 1, which, by the way, is twice of 2m plus 2 times m times m. Right. Where 2m plus 2 times m is a integer, right? Thus, x squared minus 1 is even. And just to be clear, what does that mean then? That is to say, x squared minus 1 is not odd, right? Hence, the claim follows by contraposition. Or you could say, using proof by contrapositive, we're done. It's another way you could word that last sentence.
If x was 2, would it still count as or I guess
If x was 2.
never mind, it didn't make sense. Because
Yes.
I guess I was just thinking if x was small enough, it wouldn't be divisible by 8. But once it's big enough to be divisible, then it's
Well, yeah, I mean, it can still be negative, and, well, I guess x squared minus 1 is, I mean, it's only negative when x is 0, and otherwise it's 0 at plus or minus 1, and then it's always positive above that, I suppose. Anyway, yeah. All right, so that's one. Let's see here. So we haven't, I don't think we've done a biconditional proof yet. We should do one of those. Let's go for that. So this is my example 2.5.1, example 4. It says let A be an element of the integers, period. Then A is odd if and only if. Well, let me write it out. I'm going to write it as it is in the notes. If and only if A plus 1 is even. All right. So this is we're asked here to prove a biconditional, right? So that if and only if means that we have to establish, both conditions, right? And remember, we proved this tautology that we had P if and only if Q what? Was logically equivalent to what? It was logically equivalent to P implies Q, right? And Q implies P, right? We need both. So the proof has two stages, right? The forward direction and the converse direction. So as a point of mathematical sort of custom, I usually put a little parentheses with a forward implication at the start of my proof to announce to the reader, hey, I'm working on the forward direction here. So we're going to suppose A is odd. Right. Then there exists m in the integers such that what? A is equal to 2m plus 1. Period. Therefore, A plus 1 is equal to 2m plus 2, which, by the way, is 2 times m plus 1, where m plus 1 is an integer. Hence what? I'll throw in a thus here. Thus, a plus 1 is what? Not odd this time. We've shown it's twice m plus 1 here, right? A was odd. A plus 1 is 2 times m plus 1, which means that a plus 1 is even. All right, that completes the forward direction of the proof. And the converse direction, I'll put an arrow like this. So conversely, suppose A is even, right? Then what? Then there exists, I'll use a j this time for a change of pace, j in the integers, such that A is equal to twice j. Then A plus 1 is 2j plus 1, hence A plus 1 is odd. Yep. Oh, I'm sorry. You're right. I'm an idiot. Thank you. I lost track of where I was. So yes, this is wrong. What do I need to do to fix it? I'm supposed to do what? A plus 1. I'll make the correction here. I'll make the correction in red so you guys can see it better. Thank you. Sorry, my brain skipped a beat here. We're supposed to suppose A plus 1 is even, right? Not A, but A plus 1. That means that A plus 1 is equal to what? 2j. Then let me fix my next sentence there. Not many know this, but you can erase with tea. Coffee also works very well. The only bad part is now I have to wait for the board to dry. However, I also have this. There we go. So we're trying to get A is odd, right? So consider A is equal to A plus 1 minus 1, right? Can we agree? Which is equal to 2j minus 1, right? Which, let's see here. Can we rewrite that as, let's see here, this is twice something plus 1. So what goes in the parentheses? You guys help me out. I know there's a j that goes there, right? But if I want to have a minus 1 on the left-hand side, and I have to put this plus 1 here, what does that force me to put in the parentheses? Minus 1? Okay, very good. So then what? Notice that j minus 1 is a what? An integer, thus A is odd. It's like, wow, this seems so easy the first time. If if you make the right kind of mistake, it can make proofs way easier. But don't be like me, don't do that. Yeah.
I have a question about
Oh no, what have I done? What's that?
example 3.
Uh-huh. Oh.
So, yeah, so we started out positive.
Yeah.
Does the conclusion then, is that just implying that because x squared minus 1 is even, then 8 divides x squared minus 1?
Oh no, what have I done? Oh man. Oh, my brain is not working today. This is bad. I guess I should have looked at my notes. The notes actually have the great proof there, don't they? All right, so what have we... I guess we need to return to example 3 and finish it, don't we? Yeah, thanks, guys. If you see something, say something. Much appreciated. Can we fix this? Where are we at the moment? Oh, and let's finish example 4. Are we good on example 4? So we proved both directions. All right, so what have I established so far? I've just established that x squared minus 1 is even. I mean, I guess that's great, but not what we were trying to prove, is it? Rats. All right, well, I think I know how we can fix this. We will... So, I mean, this is... But what claim follows here? What have I actually proved here? I've actually just proved... What's my claim that I proved? The claim that I proved is that x squared minus 1 sorry, it's breaking my brain. I proved x not even implies x squared minus 1 is not odd. So I guess that means x squared minus 1 odd implies that x is even. So I mean, if you look at this, I do think we proved something interesting. It's just not what we set out to prove, right? I believe this is the claim that we've proved. If I have not made yet another error today, would we agree that this is the claim I've actually proved in this argument? See, because I assumed that x is not even, and I proved that that implies that x squared minus 1 is not odd. So the contrapositive that I've actually established, I mean, the proof by contraposition, using proof by contraposition here, what I've actually proved is that x squared minus 1 odd implies x is even. So that's a lovely claim, but that's not what we set out to prove, right? So, okay. So let me jump in right here. Tell you what, just for the sake of clarity, I'm going to start the proof over because I think that anything other than that is probably going to lead to too much suffering. All right, so the proof is going to start out pretty much the same way we did. We're going to suppose x is an odd integer, all right? So example 3, corrected. Okay. My apologies. All right, so we're going to assume x is not even. Thus, x is odd, and so there exists m in the integers such that x is equal to 2m plus 1. Consider x squared minus 1. So what got me into trouble last time is my love of factoring. I love factoring too much. So I think if we had looked, well, anyway, shut up. So we've got 2m plus 1 squared minus 1, right? And so what happens there if I just multiply that out? I get what? I get a 4m squared plus 4m plus 1 minus 1. So I'm trying to find Oh, yes. All right, here we go. I'm like, what's weirding me out here is I'm not seeing an 8, right? So that's a little bit troubling to me, but we have to remember last class at this point. Okay, so we've got a 4 times, we can factor an m out, and that gives us an m plus 1, right? But do you remember last class we proved something about the product of successive integers? What did we prove? If you take two integers and two successive integers, like these are successive integers, m and m plus 1, right? That has to be what?
Even.
It has to be even. So we did prove that last time, right? My bad. So this is 4 times 2k using lemma that m times m plus 1 is even for any m in the integers, right? So if I proved that last class, great. I think I did. If I didn't, we can easily prove that as a separate example, all right? So then what do we have? We have 8 times k, right? Thus, 8 divides x squared minus 1, right? Which means that, 8 does not divide x squared minus 1 is false, right? Which is to say that we've taken not q and we've established not p, right? So this shows not p is true. Right, so we've now established that not q implies not p, right? Has been argued. This isn't technically part of the, this is a parenthetical comment, guys. This isn't really part of the proof here, in my blue parentheses. But then we can conclude that using proof by contrapositive, 8 does not divide, that if 8 does not divide x squared minus 1, then x is even. So there's a few moving parts in this proof, right? We have to know this little lemma that the product of successive integers is even, right? How would you prove that? I don't want to write it out, but the way the proof of this is done is you take m, right? If m is an even number, then you've got 2k times 2k plus 1, which is, you can factor a 2 out, so it's even. On the other hand, if m is odd, you have m is equal to 2k plus 1, which gives you 2k plus 1 times 2k plus 2. Again, you can factor a 2 out of the second factor. So in both cases, you can factor a 2 out of m times m plus 1, which suffices to prove that the product of successive integers is even, right? So, any questions? Thank you. The questions in here have been great because I have done some dumb stuff today. Goodness gracious. Oh, so sorry, guys. Let's see how much of class time I've burnt on my stupidity. All right. So you guys have any questions before I find the next proof in here? Let's see. All right, I think it would be healthy for us to do a proof involving an inequality. So I've got one like that for us. So this is kind of a different, we've done a lot of proofs involving odd and even, obviously, at this point. I think I've pretty much shown you a pretty decent sampling of those kinds of proofs, right? So in the time that remains, I want to talk to you about talk to you about inequalities, and I think I'd like to also try to do something a little bit more adventurous and possibly interesting, and talk about the structure of rational numbers. Maybe I should start with that. Do you guys remember a different way you've looked at rational numbers? I mean, we defined them in here as ratios of integers, right? Do you recall a different definition from any other class? Anybody? Nobody?
It either has a finite number of decimal places or it has a repeating decimal.
Right. So in the case it has a finite, it still has a repeating decimal. It's just the repeating decimal is 0. Right. So yeah, we can say that we can characterize a rational number in terms of its decimal expansion. Right. A rational number is one for which eventually the decimal expansion is repeating forever and ever. So it might be interesting to think about that for a minute, right? So let's see here. So this is kind of a digression. So I'm going to remind you a little bit of Calculus 2. So it's not really a digression. This is stuff you guys are supposed to know, but you've probably forgotten. Maybe. And so let me start out here with definition. So A1 plus A2 plus ... is equal to the limit as n goes to infinity of the sum I equals 1 to n of A sub I if this limit exists, right? So we talk about Sn equal to the sum I equals 1 to n of A sub I as the nth partial sum, right? So a series converges if and only if the nth partial sum is a convergent sequence, right? This was our definition of convergent series in Calculus 2. So perhaps the most important convergent series is the geometric series, right? So an example of this, what example am I on? I've erased all my examples, so I've lost track. 5? Thanks. So check this out. So example 5, if we have A plus AR squared plus ... this is the so-called geometric series, right? If I write that out, it's the sum, I guess I could say I equals 1 to n of A r to the, I guess I minus 1 in my current notation. Oh, my bad. Let's say, we usually write this, I'll get it right eventually here, guys. Sum n equals 1 to infinity of AR to the n minus 1. That's our usual notation. My bad. Okay, great. So here, the nth partial sum is what? A plus AR plus ... plus what? AR to the n minus 1, right? And the thing is, if we take this and we multiply by r times Sn is what? AR squared, AR to the n, right? And if we take those two we take those two formulas and we subtract them, right? What do we get? Meaning I subtract the left-hand side from the left-hand side, I get Sn minus RSN. And on the right-hand side, we get a bunch of canceling, right? So the canceling, I end up with A minus AR to the power n, right? So lo and behold, this gives me S sub n is equal to a times 1 minus r to the n divided by 1 minus r. Now that assumes what? To make that algebra step, what do I need?
Minus r is not 0?
Right, yeah, well, nope. I need that r is not equal to what?
1.
R is not equal to 1. Now, we can prove, eventually we will prove in here probably. We can show that the limit, let me write it this way. We can show that, r to the n goes to 0 as n goes to infinity, provided that the absolute value of r is less than 1. So in that context, we have the following. We have if the absolute value of the ratio of the geometric series is less than 1, then the limit as n goes to infinity of Sn, right, it's equal to the limit as n goes to infinity of this lovely formula up here, over here, right? And then by all the usual limit laws, we have that the r to the n term is going to 0. Everything else in here is a constant, so we're just left with the result that hopefully you know, which is a over 1 minus r. Right? So I'm giving you a proof that the geometric series converges to a over 1 minus r. And that's actually true if and only if the the ratio of the series is less than 1. So this is the geometric series. Right? Geometric series result. Now the if and only if, there's more to say there. Like I've just showed you that if the ratio is less than 1 in magnitude, that implies it's convergent. To show that it diverges otherwise, we rely on something called the nth term test. All right. So we'll talk about that much later in this course, but probably. All right, so that's just a reminder. So example 6, if I have, let's say, I don't know, 1 plus, 1/7, not 1/7, what's wrong with me here? Fine. 1 plus 1/7 plus 1/70 plus 1 over 700 plus 1 over 7,000 plus dot dot dot. Can you rewrite this as an exact fraction? So I'm just taking a break for a second here from the proofs that we've been doing, if you guys don't mind. So identify this part as a geometric series, right? If you look at this, we have 1/7, right, is my A, and my R is equal to what? 1/10, right? 1/10, yeah. So what that means by the geometric series result is this is really just the number 1 plus 1/7 divided by 1 minus 1/10, also known as 1 plus, 1/7 over, I guess that's 9/10, right? Flip it, you got 1 plus 10 divided by 7 times 9, also known as 63. And of course we can rewrite that as 73 over 63, as you can see, a rational number. So we could formalize this proof if I wanted to burn more class time on it, and we could show that if you have a repeating decimal, right? If your number has the form of a repeating decimal, we can prove that it's a rational number, right? Because we can just apply the geometric series to the repeating decimal part, take that part, make it into a fraction with the geometric series, and then add the part that came before it, right? Now the proof to actually do that would require us introducing some notation, which would be kind of like a pain, right? Like that's easy to say, it's harder to write down the actual proof because we'd have to formulate how long is the repeating decimal, right? And we have to come to terms with what's the ratio given the length of that repeating decimal, right? It would take me about 20 minutes to do that carefully, but we could do it. We have the technology to do it here. So I think it's a reasonable, but I wouldn't say I proved this in here, but you know, this is a claim. If X is an element of Q, well, that's not really what I've just argued. I've argued that if X has an eventually repeating decimal expansion, then X is an element of the rational numbers, right? Can you see how to use the geometric series in reverse to rewrite a given rational number as an unending decimal? I'm not sure. Like the reverse direction to this claim is if X is a rational number, then it has a repeating decimal. How would you prove that? See, that's a different claim, isn't it? Something to think about. I'm going to leave it at that for now. So I don't know, I was just kind of mulling over this before class a little bit. I haven't finished these proofs or anything. I was just starting to kind of toy around with it, and I haven't searched for the best proof yet. But you know, the natural question to ask, if you're in this class, is like, how would we prove that pi is not a rational number, right? Or how would we prove that e is not a rational number? Any ideas? Now, I'm not sure this is an idea I have, right? So this is just a conjecture, all right? A conjecture is something that you're not 100% sure of, but you think has got some mathematical, if it's a mathematical conjecture, it's got some kind of truth to it. So here's my suspicion. If we define E as equal to the sum n equals 0 to infinity of 1 over n factorial. That's a reasonable definition, you see, because the power series for the exponential is the same thing with x to the n tacked onto it, right? So this is exactly e to the 1 if we look at the Maclaurin series for the exponential. You guys don't know what I'm talking about. I'm reminding you this is some calculus 2 that we did at some point, right? This thing. You can take this as the definition of the exponential, and if you do that, it also forms a reasonable definition of the number e, right? E to the 1, plug 1 into this power series that defines e, right? So I'm wondering, if I study that, could I show that it can't be a repeating decimal then, from the basis of this? I don't know, this is just an idea. I'm not sure how that works. I have assigned a homework problem in Calculus 2 before that proves that E is not a rational number. All right, I think I've chased this rabbit long enough. Let me get back to the world of inequalities here. So I do have another example for today. So my example 7. So here's the claim. Is this: if x and y are positive and they're real numbers, then x plus y over 2 is greater than or equal to the square root of xy. So that's a claim. I don't think it's by any means obvious, but so when I'm faced with something, so like a lot of the thing is the proofs we've done up to this point in here, for the most part they've been pretty obvious unless I made a mistake which made them unclear, right? And if you go back and undo my mistake, you'll you should realize it was actually pretty simple, right? Modulo me chasing that rabbit. Not sure that's as true here. So when I'm faced with something like this, what I'll do is I'll work on it, right? And that work I do is not part of the proof. It's just scratch work, right? So like for this one, what I'm going to do is I'm going to square this inequality. So if I square that, I have x plus y over 2 squared greater than or equal to square root of xy squared, right? Which then gives me x squared plus 2xy plus y squared over 4 greater than or equal to xy. Which then, if I multiply by 4, gives me x squared plus 2xy plus y squared greater than or equal to 4xy. Which then gives me x squared minus 2xy plus y squared greater than or equal to 0. Which then gives me x minus y squared greater than or equal to 0. All right? This gives me hope, because I've taken the thing I'm trying to prove, right? I've taken the thing I'm trying to prove, and I have done some steps that show that you can get to it logically. You can logically connect it to something that we know. What do we know in here about inequalities? Well, hopefully in the remainder of class time, I'll tell you a little bit more about that. But one of the things we know, so we can take this as a basic starting point. So I'm going to show you the proof over here. So here's the proof. Let x and y be elements of the reals with x and y positive, right? X and y greater than 0. Notice x minus y is a real number. Thus, any real number squared is non-negative. It's greater than or equal to 0. That's my starting point, because this is what I know is true. Right? What's my next step? I'm going to give it as this is a column stacked kind of proof, all right? So first of all, x minus y squared greater than or equal to 0. That implies what? That implies x squared minus 2xy plus y squared is greater than or equal to 0. Yes, I'm working backwards, right? But it's important that we work backwards and not just say proved over there. If at any point you find yourself writing 1 equals 1 proved, you've done something very wrong in here. Like, that is not a proof. You may have been taught that was a proof in high school at some point, but you need a refund. Or as Dr. Sprano often says, you've been cheated. Anyway, so this then implies that x squared plus 2xy plus y squared is greater than or equal to 4xy, right? So we added 4xy to both sides. That is an operation that's allowed on inequalities, right? We can add to both sides of an inequality. Multiplication with inequalities, that's much riskier, right? That's much riskier. So what's next? This implies that x plus y squared divided by 4 is greater than or equal to xy. I can divide an inequality by 4 because the inequality, 4 is positive, right? So I don't spoil the inequality. Then what? At this point, I'm going to take a break from my column stacking and say some words here. Since x and y are positive, we find x plus y and also xy are positive. Thus, the square root of x plus y squared, which, by the way, is equal to the absolute value of x plus y, is equal to x plus y. And the square root of xy is a real number. Thus, the square root of x plus y squared divided by 4 is greater than or equal to the square root of xy, which finally implies that x plus y over 2 is greater than or equal to the square root of xy, which is what we set out to prove. Now, there's a lemma I just used there that we need to develop more. We need to develop this lemma more completely. There's something I need to, I'll put it in red here, as, you know, the square root is an increasing function on 0 to infinity. See, because do you notice logically what's going on here? I went from here, right? And I'm saying that this implies that right there. Why is that legitimate? Can you take the square root of an inequality? Can you take the natural log of an inequality? Can you take the exponential of an inequality? Can you take the sine of an inequality? Which operations are allowed for inequalities, right? Let's talk about this. So, let me see here. Let me clear myself some board room here. So if you're thirsting for some proofs that are a little bit harder, this is not a bad place to start. Like, this is nothing. I don't think proving E is not rational is an easy thing to prove, right? I'd have to really stop and think about that. But I have a suspicion that this repeating decimal business I just showed you could be used in part to attack it. All right. So we need to talk about inequalities, how to solve them and everything. But I think one lemma that would be useful for us is really to remind you of a definition. If A is less than B implies that f of A is less than f of B for all A and B in U, which is a subset of the reals, then f is increasing on U. And I really should say strictly increasing. Right? If we just had increasing, we'd add less than or equal to. All right, less than or equal to both of those. On the other hand, if A is less than B implies that f of A is greater than f of B, you know, for all AB in U, which is a subset of the reals, then f is strictly decreasing on U. So, in the interests of freeing you guys to make efficient arguments, it's super helpful to know some calculus here, right?